Assalamualaikum warahmatullahi wabarakatuh. In this video, we are going to discuss about two concepts. Number one, the determinant of a 2 by 2 matrix, the determinant. And after that, we are going to discuss about the inverse, okay, of 2 by 2 matrix also. And I hope, okay, all of you understand what we mean by a matrix of size 2 by 2. This first number 2 is for the number of row. The number of row. And for this second number 2 is for the number of column. For the number of column of that matrix. 2 by 2 means, okay, the matrix having 2 rows and 2 column. So in this video, we are going to specifically discussing the determinant and the inverse only for 2 by 2 matrix. All right. So first of all, maybe you want to get some idea actually what is the concept determinant of a matrix mean. It's just a number, you know. It's just a number. Determinant is just a number that can be calculated from any square matrix. Okay, I want to stress the word square here because only square matrix having determinant. So whenever we talk about determinant of a matrix, that matrix must be a square matrix. Square matrix here means that matrix having the same number of rows with the same number of column. If the number of rows is 2, okay, the number of column also must be 2. And in this video, we are going to talk specifically for a very special square matrix that is 2 by 2, meaning the number of row must be 2 and the number of column also must be 2. So then maybe you want to know what is actually the use of determinant of a matrix. Okay, there are a couple of usage of determinant. Number one, we can use determinant, okay, to determine okay, whether if a matrix, I mean a square matrix having inverse or not, right? That's one of the use of determinant. By knowing the determinant, then we can tell whether that matrix having inverse or not. Okay, we are going to talk about inverse in this video also. Number two, we also can use determinant to find the area of a parallelogram. Okay, we can use determinant to find the area of a parallelogram. Okay, in 2 dimension. Okay, if we talk about in 3 dimension, we are going to talk about the volume of a solid that we call parallel pipe in 3 dimension. Okay, we can use determinant also to find the volume of a parallel pipe. In 2D, 2 dimension, we can find the area of a parallelogram. Okay, parallelogram. Now, the next question is, what is the notation that we use to represent a determinant? Okay, we can write like this for determinant of, for example, matrix A, or also we can write like this. A, okay, with two lines on both sides, on the left and on the right. Okay, this will represent the determinant of a matrix. For example, matrix A. This is the way how we write the determinant of a matrix. All right, so how to calculate the next question? That is how to calculate the determinant of a 2 by 2 matrix. Meaning to say, what is, if any, the formula of determinant of a 2 by 2 matrix? Okay, luckily, yes, we have a formula. Suppose that we have a matrix A with symbol, for example, A, B, having element A, B, C, and D. Okay, in the first row, we have A, B. Second row, we have C, D. Now, if that is the matrix A, then the determinant of the matrix A is equal to A multiplied by D minus B multiplied by C. That's the formula to find the determinant of 2 by 2 matrix. All right. Maybe you can give one example here so that we can get the idea how to find the determinant of one particular matrix. Now, suppose that we give this matrix B having element like this. Let's give something like 1, 3 in the first row, and maybe we have 1 there also, and we have 2 over here. So B equal to 1, 3, 1, 2. The question is, what is the determinant of B? So the determinant of B will be equal to A times D. A in this case is 1, D is equal to 2. Okay, please notice the position of these numbers. So we have to multiply 1 multiplied by 2, okay, minus 3 multiplied by 1. So let's simplify this. 2 times 1 is 2, and 3 times 1 is 3. And 2 minus 3 is negative 1. Okay, so that is the determinant of matrix B. What is the value? Negative 1, as we mentioned in a few minutes ago, that the determinant is a number. Whenever we calculate a determinant of a matrix, we're supposed to get one single number. And that number can be negative like this. Okay, negative 1. Is it okay to have the value of a determinant negative number? Yes, exactly. We can have. No problem with that. Negative number, fraction. In fact, we can have numbers like pi, that is an example of a irrational number. We cannot have also the what we call the determinant of that types of value. Any real number, okay, can be accepted as the value of the determinant. One square matrix, okay, having one determinant, okay, 1 to 1 like that. Now let's see maybe what happened, what happened when the determinant is 0. Because as we say, that determinant can be any number, right? Now what happened, because 0 is a very special number, what happened if the determinant is 0? Okay, and we previously mentioned that the use of determinant is to determine whether that matrix having inverse or not. Now, what happened when the determinant is 0 is that, yeah, that matrix having no inverse. Okay, when that is, we say if the determinant of matrix A is equal to 0, then the matrix is singular. What we mean by singular here is that the matrix having no inverse, or sometimes we say not invertible, like this. The matrix is not invertible means the inverse does not exist. So that's the significance of the determinant. If we know at the beginning that the determinant is 0, then we know that the inverse does not exist. So we are not going to look for the inverse because it does not exist. So it's very important for us to decide first what is the value of the determinant. Especially if we find out that the determinant of A is equal to 0, then automatically we know that the matrix having no inverse, or that matrix is a singular matrix. It is not invertible. Okay, under what condition we are going to answer this question now? Under what condition the determinant is 0? There are three conditions. Number one, condition here means looking at the element of the matrix. Number one, if the matrix A having 0, 0 row. This is the first condition. What we mean by 0 row is that that particular row having all zeros in that row. Okay, whenever a matrix having a 0 row, then the determinant is 0. Okay, not only 0 row, also 0 column. Number two, okay, a matrix B, if matrix B having having 0 column, meaning to say in that column all the numbers are all 0. So whenever we have that situation, we say that we have 0 column, and whenever we have a 0 column, then the determinant of that matrix is 0. Now number three, the third condition, okay, where we have determinant is 0 is that if a row is a multiple of the other row. This is okay. This is three. I mean, these are the what we call the condition. Okay, where it will make the determinant equal to 0. That is number one. Whenever we have 0 row, then the determinant is equal to 0. Or maybe we have a 0 column, then that will also affect the determinant. The determinant becomes 0. Or we have one row is a multiple of the other row. That will make the determinant 0 also. Okay, maybe we can give examples, some example according to those three conditions that will make the determinant equal to 0. Number one, for the case when we have 0 row. Number one, maybe we can write matrix A having 0 row. For example, we have 1, 2 there, and we have the second row, all elements are all 0 like that. And if we have a matrix like this, that is whenever we have a 0 row, then the determinant of this matrix is 0. We can calculate, the determinant of A is equal to A times D, that is 1 times 0, okay, minus B times C, 2 times 0. Okay, do you see that this is 0 minus 0 there? We got 0, right? Okay, that's true. Okay, in this case, we have the determinant is equal to 0 because one of the row is a 0 row. Okay, number two, maybe you can have matrix B having 0 column. That is, maybe we have 3, 5 here, and maybe for the second column, we have 0, 0 like this. The determinant of B, you can check it out. The determinant of B also equal to 0. Now, for the third case, where one row is a multiple of the other row. For example, we have matrix C equal to, let's do like this, maybe 1 and negative 2 in the first row. For the second row, we have 2 and we have negative 4. Do you see that the second row is double of the first row? Multiple of the first row. That is, if we multiply the first row by 2, we have the second row. Okay, in this case, if we calculate the determinant of matrix C, we can get also the determinant is equal to 0 also, because okay, the second row is a multiple of the first row. Okay, I hope you understand what we mean by the third condition. Okay, so there is a relationship, okay, between the determinant of a matrix and the determinant of its transpose. I hope you still remember what we mean by a transpose of a matrix, right? The condition is like this. I mean, the relationship between the determinant of matrix and its transpose is like this. That is, suppose that the matrix is A, okay, the determinant of A is actually the same as the determinant of its transpose. Meaning, we find the determinant of A, right? We get a number. Then we transpose the matrix, okay? And then we find the determinant of that transpose. And we get the same value. For example, if we have matrix B equal to, suppose we have 2, 1, 3, 4 like this. That is B. Let's transpose B. Okay, B transpose. Let's write down B transpose. Okay, the main diagonal number is still the same. We have 2 here. We have 2 and we have 1 there. All right. Now, when we transpose it, will become, okay, 4. This number 3 become 4 and 4 becomes 3 like this. Column become row and row becomes column. Now let's find the determinant of matrix B. Okay, 2 times 1, 2, minus 4 times 3 is 12, is equal to minus 10. Alright. Now, what is the determinant of B transpose? Equal to 2 times 1 is 2, 3 times 4 is 12. We have to subtract, right? So 2 minus 12 is negative 10. You see? The transpose of B, the determinant of B and the determinant of B transpose, we get the same number. Okay, over here we have 10. Here also we have 10. So, we conclude that the determinant of B and the determinant of B transpose always the same. Okay, equal sign, is it? Meaning the value is the same. Okay, now let's talk about, after we discuss a little bit about the determinant of a matrix. Okay, the next concept related to determinant is inverse. Inverse of a 2 by 2 matrix. Yes. So how to calculate? Okay, this is the big question. How to calculate the inverse of a 2 by 2 matrix? Yes, luckily we have the formula, and the formula related to the determinant. That's why we talk about the determinant first, and then we talk about the inverse of the matrix. The formula is like this, and the symbol for the inverse is A. We have to the power negative 1. Okay, doesn't mean that A to the power negative 1. This is just the notation to represent the inverse of matrix A. A to the power negative 1 is equal to, if A is given like this, A, B, C, D, okay, if A is like that, A, B in the first row, C, D in the second row, A inverse will be 1 over the determinant of A multiplied by A and D change position. We have D at the position 1, 1 and A at the position 2, 2. B and C keep at the same position but with negative sign like that. Yes, this is the formula to find the inverse of a 2 by 2 matrix. That is 1 over the determinant of A multiplied by, first row we have D negative B, and the second row we have negative C and A. Alright, maybe we can give an example of finding an inverse of a matrix. Let's give another matrix. Let's suppose we have D, matrix D equal to, let's see, let's see, 3 here, and we have 1 there, we have 2 there, and we have 1 also here. All right. Now again, please take note that over here is actually the determinant of A, right? We need to find the determinant first. Okay, this is determinant of A, so we need to find the determinant. In the formula of finding the inverse, we need to find the determinant of that matrix first. So what we need to do first is that we have to find what is determinant of D. Alright, so 3 times 1 minus 1 times 2. This is equal to 3 minus 2 is equal to 1. Yes, we are very lucky here because we have the determinant of D is equal to 1 and 1 over 1 is equal to 1. So it's become, our calculation become much simpler. So we have to find the inverse of D is equal to, all right, 1 over the determinant of D, that is 1 over 1 multiplied by, okay, what is D in this case? D is 1. Okay, A is equal to 3, B is 1, and C is 2. And we have to put, well, or we have to include the negative sign, like that. Now the value of, or the matrix of inverse, or the inverse matrix of D is equal to, okay, multiplied by 1, we'll have the same number here, won't change anything. We have 1, negative 1, and we have negative 2, we have 3. Okay, that will be the inverse of matrix D. This is D, okay, this is D, and this is the inverse of D, this one. This is the inverse of D. The matrix D is 3, 1, 2, 1, and the inverse of D is 1, negative 2, okay, and negative 2, 3. Like that. Okay, now maybe you would like to know the relationship between a matrix with its inverse. Is there any relationship between the matrix and its inverse? For example, D and D inverse. Is there any relationship between them? The answer is yes. That is, if we multiply, okay, D for example, multiply by D inverse, we'll get a very special matrix that we call matrix I. That is matrix identity or identity matrix. Okay, we can also get I if we multiply D up front, okay, with D, like this, multiply, put dot sign to represent multiplication. That is, a matrix, if we multiply by its inverse, we'll get identity matrix. Okay, maybe we can verify this by looking at the example for D just now that we use, that is D equal to, let's copy D, and also we already have our D inverse from the previous example. Let's go back and see our matrix D. 3, 1, 2, 1 for D. Okay, 3, 1, 2, 1. And for D inverse, we already calculate 1, negative 1, and negative 2, 3. 1, negative 1, 1, negative 1, and negative 2, 3. Like this. Yeah. 1, negative 1, and negative 2, 3. Yeah. Now let's check our calculation whether we have this matrix D inverse is correct or not from our previous calculation. Okay, let's check it out by using multiplication D multiplied by D inverse and see whether we get the identity matrix. I hope you still remember what we mean by identity matrix. Yeah, this is identity matrix. Let me write it down. Okay, up here. This is the identity matrix for 2 by 2 matrix. That is 1, 0, 0, 1. This is what we call identity matrix. Identity matrix. Okay, if we multiply D by D inverse, we supposed to get the identity matrix and see whether we get identity matrix or not. Okay, in this example here. Okay, D, we copy down 3, 1 and 2, 1. Multiply by D inverse. We have 1, negative 1, negative 2, and 3. I hope you still remember how to do multiplication of 2 by 2 matrix. Okay, 2 by 2, okay, multiply by 2 by 2 matrix. I hope you still remember how you do that. Now, let's see. What's the answer? Now, 3 times 1, okay, 3 times 1 is 3. 1 times negative 2 is negative 2. So, 3 minus 2 is 1 there. Okay, now for the second number, in the first row, we have 3 times negative 1 is negative 2, negative 3. 1 times 3 is 3. So 3 minus negative 3 plus 3 is 0 there. 2 minus 2 is 0. And we have, okay, in this position, we have 2 times negative 1 is negative 2. 1 times 3 is 3. 3 minus 2 is equal to 1. Yes, this is identity matrix. 1 0 0 1. Yes, so we have the what we call the identity matrix. Okay, therefore that shows that the D inverse, yeah, D inverse that we get just now from our calculation is correct. Yes, so that is the correct inverse of D. That is 1, negative 1, negative 2, and 3. That is a correct inverse of matrix D. Before we done with discussing about the determinant and the inverse of matrix, that write down some exercises so that you can try it out whenever you have free time. Okay, the exercises is asking us to find the inverse of the following matrices. Okay, I'm going to give you three matrices. Number one, okay, this matrix A equal to negative 1, we have 3, and we have negative 2 and 4. Find the inverse of this matrix, okay, by using the formula that I discussed a few minutes ago. Now for question number 2, the matrix is matrix B, and the element of matrix B is like this: 2, negative 3, and negative 2 and 3, like that. Now, for the last exercise is part C, that is matrix C equal to, we have 2, 1, 2, 1, and 1, negative 1. Find the inverse of this matrix. Okay, if exists, because we already discussed and mentioned that some matrix, they don't have inverse. That is, they are singular matrix. Whenever they are singular, meaning they have no inverse. No inverse because the determinant is equal to 0. Alright, I think that's all for now. See you next time. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.